Now when we are working with complex numbers, we've got the standard format that we want to write them in, so z equals a plus bi. And that's fairly straightforward when it comes to adding, subtracting, multiplying or dividing any pair of complex numbers. But we've got to ask ourselves about two set operations. First one being the division of a pair of complex numbers. The second one being what happens if we take the square root of a complex number. We always want to try and write the complex numbers in that standard format, z equals a plus bi, but initially looking at it, that's not possible when we do these operations. So what we've got to say to ourselves is, how would we do that for a calculation of that format? If you look at the calculation here, the division of two complex numbers, if I was to do what I did in a previous bit of work when I was dividing by a single digit number, so if I had 3 plus 4i divided by just 2, I could separate that into two set fractions and still have it in that standard format of z equals a plus bi. However, if I split it off this way with this one, the exact same format in the exact same way, I'm going to end up with a complex number as the denominator of both fractions. So I'm not going to be able to write it in that standard format. So we have to ask ourselves, right, how can I do this sort of calculation and get it in the form of z equals a plus bi? Similarly, we've got to ask ourselves, how would we do that if we took a square root, so this sort of calculation here? Because square root of 5 plus 12i, well, there's a square root involved in that. That's not written in the standard format. And we can't just simply split it and say, fine, well, it's the square root of 5 plus the square root of 12i. We can't just say that. That is naughty, naughty maths. So we have to say to ourselves, how would I deal with this sort of calculation? That one requires a little bit more work, but it's a bit of number theory we're able to handle. Let's focus on this bit here to begin with. So 3 plus 4i over 2 minus I. How do we get rid of the denominator for that? Well, what we have to do is jump back to some maths that we did previously at National 5 level. So let's imagine I went back and I said to you, can you multiply it and simplify 3x plus 2y times 3x minus 2y? Well, if I were to do that, I get 9x squared take away 6xy plus 6xy take away 4y squared. And what would happen is these two parts here in the middle would disappear, and I'd end up with 9x squared take away 4y squared. This is our difference of two squares. So if you remember, we've got a squared minus b squared equals a plus b, a minus b. Now these two brackets are what are called the conjugate, i.e. the sign in the middle is the opposite of each other. And we notice that if we multiply these conjugates together, what we end up with is the square of the elements in the bracket subtracted from one another. If we were to apply this theory to a complex number, so let's say 3 take away I, and I was to multiply that by its conjugate, 3 plus I, what I'd end up with is I'd get 9 plus 3i minus 3i minus I squared. So that would end up giving me 9 plus 3i minus 3i would disappear. I squared is negative 1, so it would be minus minus 1. That would be plus 1, so I'd get 10. So what I've done there is I've managed to get rid of the imaginary part of my complex number and end up with just an integer value. Now if I was to somehow use this fact to turn the denominator into an integer value, that would be great because I could get rid of the complex number on the denominator and split it into the format I want. And this is how we do it. What we do is we could take our fraction, so again, let's just say add 3 plus I over 2 minus I. If I were to take the fraction and multiply the top and the bottom by the conjugate of this, so that would be 2 plus I over 2 plus I would get rid of the imaginary number in the denominator and I could then separate it the way that I want. Now note, I've multiplied the top and the bottom by the 2 plus I over 2 plus I because remember this simply cancels to 1. So as long as I do it to the top and the bottom, I'm going to get what I want. It'll keep the imaginary number in the top, it'll keep the imaginary number in the numerator of the fraction, which is fine. It's allowed to be there for us to split it into the format, but it gets rid of it in the denominator, which is what we want to do. So let's go back to the example I showed you at the start and let's have a look at how we'd apply it to that. So let's imagine I want to simplify 3 plus 4i over 2 minus I, and I want to write my answer in the format z equals a plus bi. Well, the first thing I'd do is I'd say to myself, right, what is the complex conjugate of the bottom? So it is the conjugate of 2 minus I. Well, that would be 2 plus I. So what I'm going to do is multiply the top and the bottom by 2 plus I. What that would then mean is on the top I've got 3 plus 4i times the 2 plus I over 2 minus I, 2 plus I. So I can take the top and the bottom, multiply them out and simplify them separately, stick it back together, and then I have my answer there. So if I look at the numerator to begin with, 3 plus 4i bracket 2 minus 2 plus I. If I multiply that out, I get 6 plus 3i plus 8i plus 4i squared. So that would then give me 6. I've got 3i plus 8i plus 11i, and then I've got 4i squared. I squared is negative 1, so I've got minus 4. So my numerator would become 2 plus 11i. My denominator, I've got 2 minus I, 2 plus I. So again, I multiply it out. Now, if at this stage you're going to do it step by step like this, that's great. Do it. So I would do 4, I then have plus 2i, minus 2i, then minus I squared. Plus 2i minus 2i disappear. I squared is negative 1. I've got 4 minus minus 1, which is 5. Great. If, though, you're able to remember that your a minus b, a plus b from before is equal to a squared minus b squared, and you're able to relatively quickly identify the a and the b and just jump into this format here, do it. I'm not going to stop you. If you got to that stage, great, it would save a little bit of time on working. So for example, I'd look at this and I'd say fine, so a is 2, b is I, so I'd do 2 squared, take away I squared, that would be 2 squared, which is 4, take away I squared, minus minus 1, which gives me my 5. So if you're able to jump to that quick stage, do it. Go for it. Nobody's going to stop you. Then stick it all back together and I write it in the format I want. So I could say fine, so I know z equals 2 plus 11i all over 5, which I could split into my format that I want there. I get 2 over 5 plus 11 over 5i. So I've got it in the format a plus bi, which I want there. Yes, a and b are fractions, but that doesn't mean anything at all. It all depends on the format that it wants, and that's me got it in that format. So there you go, and dividing by complex numbers to get it in that format, that's how we deal with it. The other problem we wanted to deal with was the square root, because we can't have a square root in it if we want it in this standard format here. So how would I go about dealing with that? Again, let's go back to what we said at the start. Square root of 5 plus 12i. And I want to know how to put that in the format that we want. So what we want to say is that I want to somehow write a plus bi being the format for the square root of 5 plus 12i. Well, this here is actually your key step to begin with. If I set a plus bi equal to that, and I then do a bit of manipulation, I can do a calculation to calculate my a and b values for here and write it in the format that I want. So if I know a plus bi is equal to square root of 5 plus 12i, what I can then do is square both sides to get rid of the square root, and I'd have a plus bi all squared equals 5 plus 12i. Now you're looking at that going, but there's a squared there now, that's still not in the same format. Well, because I've now got a bracket and I'm squaring it, I'm doing a plus bi times a plus bi. We know how to multiply two complex numbers together like that. If I do a plus bi times a plus bi, what I end up getting is a squared plus abi plus another abi plus b squared I squared. And if I simplify that, the I squared becomes negative 1. So I get a squared minus b squared plus 2abi, but I know that that is equal to 5 plus 12i. So that's equal to my standard format of a complex number for this one. What I can now do is split this into real parts and imaginary parts and equate them. If these two are equal to each other, what I'm able to then say is fine, so I know that a squared minus b squared has to be equal to 15, and I know that 2ab has to be equal to 12. For this one, just equate the coefficients. You know they both multiply by I, so that cancels. What I can then do is rejig this about, get something here representing b in terms of a or a in terms of b, substitute it back into here, get some sort of quadratic to solve for the variable I've got, and then substitute it back to get the other one. Seems like a lot of work to do just to find an a and a b, but it's a nice set of standard steps to do. So let's imagine I take this and I rearrange it so that I get b equals 12 divided by 2a, so I get 6 over a. What I can then do is take this and substitute it into here, and what I then have is a squared take away 6 over a all squared is equal to 15. What I'm then able to do is rearrange that and then see what I get. So I get a squared, 6 squared over a squared, I get take away 36 over a squared equals 15. If I multiply through by a squared, what I end up getting is I get a to the power of 4, take away 36 equals 15a squared, shift it across here, and I've got a to the power of 4, take away 15a squared, take away 36 equals 0. Now this is in the format of a quadratic, the only difference being quadratics are normally ax squared plus bx plus c equals 0. The only difference is, in this case, what would be my x is actually a squared. So if I was to solve this using the quadratic formula, what I'd be able to say is fine, so a squared equals negative b plus or minus square root of b squared minus 4ac. So a squared equals negative b, so 15, plus or minus a square root of b squared, so negative 15 squared, take away 4 times 1 times the negative 36. That would then be all over 2a, so that would then be all over 2. And if I then simplified all of that there, what I'd end up getting is that a squared equals 9. So if a squared is equal to 9, a is equal to the square root of 9, so it's either 3 or negative 3. Because remember, you've got a positive or a negative square root for it. Now that I know a being 3 or negative 3, what I can do is substitute it into here to get the associated value of b for each of the a's, and I get my answer for it. Now, a key thing you'll notice here then is I've got 2 answers for a, so logically I should get 2 answers for b. That'll give me 2 solutions to this. Well, remember, when you take a square root, you get a positive and a negative answer. So getting 2 solutions for this makes logistical sense. If I have a is equal to 3, and I substitute that into this part here, so b is equal to 6 over a, what I get is b is equal to 2. And if I have a being equal to negative 3, and substitute that into there, I get b is equal to negative 2. What that then gives me is my 2 solutions, so I get z1, let's call it that, is equal to 3 plus 2i, or z2, my second solution, is equal to negative 3 minus 2i. So I get my 2 solutions from that. This bit here though, this is your key first step. Equate it to each other, square both sides, get your quadratic for a and b, and then equate the real and the imaginary parts together. Once you've done that, you can find your a and your b, write your final answer, and just remember, look for multiple solutions because it's a square root. That's what we're after. Remember, normally square root of a number gives you a positive and a negative answer, so logistically we'll get 2 solutions for this as well. Follow the working through for that.